result, we need a force and a couple at point A. So what we're going to find, and we'll see in the picture what these mean, is that one force I'm going to call F super R, and one couple I'm going to call C sub R. This is a vector. We're going to do it in component form and then put it into polar. It doesn't specifically ask for that, but those are usually the steps we have in 2 dimensions. All right, so step 1, we want our original system, which I'm going to label as Roman numeral 1. So we have a 100-pound force acting at a 3-4-5 ratio triangle. We have this 200-pound force to the left, and we have a 150-pound force down. This is 3 feet and 3 feet. And I'll give these points letters so we can refer to them if we want to. And we need a coordinate system to do anything. So Z out, that way we can use counterclockwise as positive. So this will be equivalent to a second system that now we have to interpret what we're looking for and then draw it appropriately. Any questions on the original system? Okay, so all I did was copy it exactly with those 3 forces. Right, so I have that same bracket in my second system. However, here, this is my simplified version. So what I'm looking for is an equivalent system with a force and a couple acting at point A. So the force, as I said in the previous slide, I'm going to jump right away into writing it in component form. So Fxr and Fyr. I'm going to assume it's positive, and then at the end, see if I'm right or wrong. In reality, the force is going to be just some magnitude and direction, Fr. But I'll get to this. This is going to be harder to deal with, because then I have to use sine and cosine of this unknown angle. Just like we saw in chapter 2, this is going to be an easier way mathematically by hand to do it. Then we can get to polar form later. So I'm going to start this way, and you'll see where we end up. So there's my force acting at A. So already in component form, and a couple acting at A. I'm going to assume, for the time being, that it's positive. So counterclockwise around point A, I'll call it CR. And that's it. That's my simplified system. One force in component form right now, and one couple located at A. Right, questions about my equivalent system for this problem?
How did you get, is that anti-clockwise?
That's an assumption I made. I'm going to assume it's positive, and then let the math tell me if I'm right or wrong. Right, so you could assume that it's clockwise. You could assume this is down or left or right, up or down. I assume positive directions, and then change it at the end. It's just easier to keep track of what's happening that way. Yeah. All right, so we're going to start with the easier part. We're going to sum forces in each picture. So in picture 1, we don't look at picture 2 right now. In just picture 1, what are my sum of forces in the x direction going to be? Keep in mind, we are not in equilibrium. I'm never saying this equal to 0. Right, so negative 200. Right, so I could use that. I have the ratio triangle here, so just for the sake of my notes, using the ratio triangle, what do I use for the second part here? Right, so plus 3/5 100. Right, or if you want to find that angle and use the cosine, you can do that too. This is usually easier. And the 150 does not contribute in the x direction. So what we have is we add that together, and we get something that's not 0. It's 85 pounds. So I'm going to take this and just put it aside for the moment. I'm going to do the same procedure in my second picture, or in picture 2. So looking just at picture 2, what has a force in the x direction, or what is my right-hand side of this going to be?
Nothing.
Right, nothing. This is it. It's a simplified system. So don't overthink it. By design, this is easy, or this is a simplified way. So the only force in the x direction is FXR. And the couple, I'll point out, does not appear in our force equations. It's a couple. We'll get to it in a minute. Okay, these are the right numbers. That's right. Now we say, well, these are equivalent systems, so Fx1 must equal Fx2. So I equate this to this. Therefore, Fxr must be negative 140 pounds. Right, so I do the same thing in the y direction. So what's my right-hand side for system number 1? Not 3/5, right? 4/5, 100. Right. Right. And then that's it. The 200 doesn't affect it. So this is just a number. So the net force in the y direction is also, or is negative 70. In system 2, I only have one force by design, Fyr. I assumed it was positive. Same thing here. I assumed Fxr was negative. It turns out I was wrong. My assumption was wrong, but I'll get to that at the end. So putting these together, again, they're equivalent systems, so this must equal this. Fyr will be a negative 70 pounds. So the equivalent force should be pointing into quadrant 3, since the x component's negative by how I drew it, and the y component's negative by how I drew it. But we'll get to that once we solve for our last unknown. So this is where it gets just a little bit trickier. I'm going to look at my system 1. I'm going to take the sum of moments around one point. But whatever point I choose, I have to choose that same point in system number 2. So usually I let system 2 guide me as to what point's the easiest to take the moment about. But again, it's the same in both. It doesn't matter. I'll get the right answer. So looking at system 2, which point will be the least amount of work to take the moment about? Right, and why is it easier? Right, because here Fyr acts at A, so its moment is 0. Fxr acts at A, so it has a moment contribution of 0 also. So I'll choose A. According to picture 1, B would actually be easier because this does not contribute to the moment, this does not contribute to the moment, and the 100 also does not contribute to the moment. So B would probably be an okay choice for this also. Yeah.
If you were to use B, then you'd say that the moment is negative Fyr times the distance from A to B.
Right, so in the second one, right, so that distance, and that creates a clockwise spin. So it makes this a little bit more involved to choose B. It actually makes this much easier. So A or B, I'm going to go with A, but you'll get the same answer either way. So again, this also forces me to use A in system 2, though. All right, so in system 1, what is the moment about A going to be, piece by piece? All right, so I'll start with the 150-pound force, has a moment arm of 3. And right, it's negative because this is going to be clockwise around A. So 150 times 3, negative because it's clockwise, and counterclockwise is positive. The 200-pound force does not contribute to the moment around A because its line of action passes through A, so its moment arm is 0. We have then the 100-pound force, so it's off at an angle there. So just like we did before, I'm going to split this into horizontal, vertical components. So I'll start with the vertical component. What is the moment arm or the perpendicular distance of the vertical component of the 100-pound force to point A? Right, so this has a line of action like this. So perpendicular to A, that vertical component is 6 feet away. And that is creating a counterclockwise twist around A, so this component is positive. I also have that horizontal component. What is the horizontal component's perpendicular distance to A? Right, this is 4, so a different moment arm. And is this positive or negative around A? Right, this component is positive, but this component's negative. So you do have to pay attention to each component individually. So again, around A, if I were to apply this horizontal component, this thing would want to twist clockwise around A. So the net moment around A, negative 210 pound-feet. So I have to choose A in system 2. So looking just at that picture, what is the sum of moments around point A going to be in picture 2? Right, CR, I assumed CR was positive. And remember, couples contribute to the moment no matter where they are and the same amount. So it's just CR. I don't multiply it by any distance ever. So first of all, CR I drew at A, but I still include it. FX, FY act at A, but their perpendicular distance is 0, so that's why they don't appear in this equation. CR could be here, or here, or here, or here, or anywhere else, and we would still write CR when I sum moments around A. Also, if I wanted to take the moments around B, I would still have that CR, but now around B, I would have to include the moment caused by this Fy force. Fx passes through B, so it would not be included. So again, for simplicity, A made this very easy to write. So it's just CR, that resultant couple. All right, questions on writing either of these equations? So, by equivalent systems, this must equal this, therefore CR must be negative 210 foot-pounds. So it turned out every assumption I made was wrong, but that's okay because we're going to correct it in that last step. So I assumed counterclockwise, this is actually clockwise. I assumed quadrant 1, this is in quadrant 3. So I will now, for the sake of space on the board, I'll draw on top of this, but this should be a separate picture. I'll call it 2A. This is where I'll now draw things facing the correct direction. So my couple, I assumed it was counterclockwise. I got negative 210. So this is going to be 210 foot-pounds. And I'm going to draw it clockwise. My force at this point, I'm going to draw it as a magnitude and direction, so in polar form. So it's in quadrant 3. Going back to chapter 2, how do we put things into polar form? We have to find their magnitude and their direction. So the magnitude of force F, 140 squared plus 70 squared, the square root of that, I get 157 pounds. And its direction as measured from positive x-axis, I get 207 degrees.